problems with these Ponzi schemes, so to say. And you will see people, they will go to the bank to get loans from the bank. They will take it to those Ponzi schemes through, at these financial institutes that promise outrageously high interest rates. I'll try to talk slowly because I know I talk very fast so that everybody can understand. Yeah, because of this, I felt so bad because I don't know why people will just decide to take unnecessary risk. These Ponzi schemes, they are very, very risky because of the interest rate that is involved. And that is why I've decided to talk on this. And also, what happened last year was so disheartening. A lot of people collected their school fees from their parents, and after collecting it, they took it to Ponzi schemes to invest into it. In Nigeria, there is one we call MMM. It was very funny. My sister did it. She opened an account for me, my father, everyone, even my nephews, very, very small kids. She opened an account for everybody so that she can, invest into it. Because that MMM promised 30% interest rates, that is dollars, you understand? So people were trooping into that scheme. And funny enough, December last year, it was very funny that the schemer disappeared with the investors' money, and they were all stranded. My sister called me from Nigeria. Oh, no more money. I was like, what's happening? She told me everything. I felt so bad. That's why I decided to work on this. That was actually what motivated me to work on this. And we have several examples of Ponzi scheme initiators in history. We have Charles Ponzi. We have Bernard Madoff. We have MMM. Even the DKM in Ghana here. What happened? A lot of people invested and they couldn't recover their money. If not because Bank of Ghana came to help, to rescue the participants. So we have several of them in the world. Just to mention a few. This guy there is Charles Ponzi. He was actually the guy that named the Ponzi scheme, which was named after his own name, Ponzi. And the second guy in figure 2 is Bernard Madoff. He was actually the greatest schemer in history. He was able to last for over 20 years in the scheme, from 1980s to 2008. He really tried, right? Though he's serving his punishment in the prison as I speak. Ponzi schemes have become very rampant in the world. Several people have incurred losses, and some are still victims of the scheme. Several people, have incurred losses because of their participation, or so to say their interest in these schemes. Some mathematical methods I've tried to analyze the scheme using, like differential equation. We were just trying to focus on the Charles Ponzi, the first guy I mentioned earlier, and Bernard Madoff. They were trying to see what really happens. Why did they last long in the scheme, especially Bernard Madoff? But they haven't really looked into the dynamics of the scheme because I see Ponzi scheme, I'm trying to look at it as a disease, so to say, because it's spreading. Everyone is embracing it. It started from the developed country. Before we knew it, it's now in a developing country. And so many people are victims of this in Kenya, South Africa, Nigeria, Ghana, so many places. So I feel I should understand the dynamics of the spread of the scheme in order to know what to really do about it. Because most of the work that have been done on it, they're just looking at the financial economic issue, which is not really tackling what we really want in the financial world. And this leads to the objective of the work. To model the propagation dynamic of the spread of Ponzi scheme using an epidemiological approach, specifically an SIR model, and to characterize Ponzi scheme as a high-risk investment opportunity with high interest rates, the normal stability analysis, and finally to evaluate numerical simulations in order to investigate the effect of varying the parameter, which is the interest rate. This is a standard SIR model most of us are familiar with, where S is the susceptible, I is the infected, and R is the recovered. And we have the gamma, which are the outflow, which is the natural death rate, alpha, beta, transmission rate, and the theta there is an inflow, which is the birth rate. Now, I want to model Ponzi scheme using our SIR model. In my case, S are those who are aware of the scheme, but they've not yet invested into the scheme. Then I are those who are already investing into the scheme. And R are those who are able to get their claims, like they've successfully, been able to get their claim. Then the gamma are the natural death rate. The theta there, those are the people who are joining the S compartment. The alpha of R and beta of R, like alpha of R, this is the fraction of those who have decided to invest into the scheme. And beta of R is a fraction of those who got their claims. That is, after investing into the scheme, you've gotten your claim. So that's the fraction. Beta of R tells us the fraction of people who do not make a loss. That is, those who got their claims. And this is where loss occurs to the scheme. As a result, I'll be considering the loss distribution, which are called as beta of R. I'll be considering the frequencies of the losses as well, which are called as beta of R. Furthermore, beta of R is examined using an exponential distribution. Moreover, I assume that 1 minus beta of R, that is the fraction of those who do not get their claims, is proportional to the fraction of those who have been able to invest, like who have already invested into the scheme, those who are already interested in it, and they've gone ahead to invest into the scheme, which is the alpha of R. So showing the relationship between 1 minus beta of R and alpha of R, I have the equation 3 there. And this graph just shows the relationship. That is, as the interest rate increases, like as they increase the interest rates, the risk of investing into the scheme also increases, because this 1 minus beta of R is associated with the risk of not getting your claim. And alpha of R is associated with the risk of investing into the scheme. So this graph really explains the risk-return relationship. Now this is the model system of equations, equation 4, 5, and 6. At the steady state, there are two equilibria, the present scheme-free equilibrium and the endemic equilibrium. In order to obtain the equilibrium point of the above-mentioned equilibria, the derivative of the state vector of the model is set to 0. Hence, at the steady state, we obtain equation 7, 8, and 9. The present scheme-free equilibrium point is given as equation 10. I'm trying to, rush it out because of the time. Then the reproduction number. My colleague explained the reproduction number earlier on. When I'm talking about the reproduction number, it helps to know, if the scheme, in my own case, if the scheme will spread at the initial phase. And it also helps to know if the scheme will remain endemic, that is, if it will remain in the system or if it will collapse eventually. Hence, my reproduction number is computed in equation 11 as follows. And for the specific case under consideration, that is the exponential distribution that I'm considering, I have equation 12. If R0 is less than 1, then the point scheme-free equilibrium is locally stable. On the other hand, if R0 is greater than 1, then the endemic equilibrium is locally stable. The endemic equilibrium point is given as equation 13, 14, and 15. Now, I want to consider the local stability in terms of the interest rates, which is the small r. In this case, like I said earlier on, that for the point scheme-free to be locally stable, R0 has to be less than 1. Now, in terms of the interest rates, R, which is the interest rate, has to be less than the R star there. And the R star is the threshold value for this work. And now, considering the endemic equilibrium, for R0 to be greater than 1, R, which is the interest rate, has to be greater than this R star, which is also this threshold value. Now, we want to verify this using some numerical parameter values. And these are the assumed parameter values for this work. These values are hypothetical, please. And we're also chosen due to the condition that the k theta minus gamma, blah, 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 have to be greater than 0. So that was what helped the choice of these parameter values. Now, substituting the assumed parameter values into my work, my R star is 0.4, which means that 0.4 is 40% interest rate. It means that if any investment scheme promises more than 40% interest rate, anything could happen. And when it promises less than 40% of interest rate, anything could happen. So I tried to choose a value, 0.39, which is less than 0.4. I got my R not to be that, equation 19. And when I chose the value greater than the threshold value, which is 0.4, I got my R not to be this. You could choose a value lesser, even though if you choose one, you will have like maybe 2 point something or 1 point something, it depends. So I just decided to choose this value, really. Now this is the numerical simulation. When I try to vary the interest rate, that is looking at it from 0.2 to 0.4, less or equal to this threshold value, I noticed that a lot of people were able to obtain their results. Sorry, I'm supposed to explain something here. If you look at this, you'll see that R naught is less than 1. It means that the Ponzi scheme free equilibrium is locally stable, which means that the scheme will collapse when the interest rate is less than the threshold value. And this one says when the interest rate is greater than the threshold value, the scheme will be sustainable. But come to think of it, why do we think this is happening? We will see what happens now using the graph for the return. This is RT graph. When the interest rate is less or equal to 0.4, a lot of people were able to get their returns up to a particular peak where it starts dropping. But if we look at it, it converges to a non-zero finite value. It means that when the interest rate is less or equal to the threshold value, a lot of people will get their returns. And the possibility of getting all their returns is very, very high. But the I of T says it will collapse. Why? A lot of people tend to rush. They tend to rush into any investment scheme that promises outrageously high interest rate because they feel they will be able to get like double of their money or even more than double. So when the interest rate is not too much, you notice that so many people might not want to invest into the scheme. But the funniest part of it is, R of T is saying that if they invest in such financial institutes, they will tend to recover their money than when they invest to any scheme that promises high interest rates. And this is where most people are running to, this one, because of the high interest rates. They don't know that it's very, very risky. So we need to educate those people so that they will know that it's very, very risky when they invest into any scheme that is promising outrageously high interest rates. So looking at this, when the interest rate is above the threshold value, that is from 0.6 to 1, we could see that people were still able to recover their investments. But looking at it, converging almost towards 0 at this point. But when it's now above 1, what happens? From 1 to 5, very few people were still able to recover their investment up to a particular time. But when it's above 5, there is a transition from the concavity, the local concavity, to the convexity, to convex. You could see at this point, it's almost impossible for anyone to recover their investment because there is even no increment at all. It's very, very clear. Hence, people should be dissuaded from investing to any scheme that promises outrageously high interest rates. It might look so attractive. So many people might want to invest into this scheme, but the end product is so disastrous. In conclusion, policy scheme propagation dynamics have been formulated, and an SR epidemic model have been modeled using some loss distribution. Then we carry out a stability analysis, and finally, numerical results show that above a certain threshold of the interest rate, the number of people recovering their investments, consistently reduces, and below a certain threshold of the interest rate, up to a certain time, tau, an increasing number of people tend to recover their investments. So, some of my references. Thank you.
Thank you. Questions? Okay. That one is all right.
Thank you very much for your presentation. And I'm happy to see that you are looking at disease dynamics with investment dynamics. But the first question, do you think that the model has fully explored the dynamics of the Ponzi scheme? The second question is that if I have been recovered, or that means I have a claim or return, don't you think I am still at risk to the Ponzi scheme, meaning that you should have an arrow pointing from the recovery state back to the risk state?
Yeah.
Thank you.
Okay. Thank you very much. I understand your question very, very well. Yeah. The first one, I'm still working on it, though this is the first part. I still have another part that I didn't present here. So yeah. Because of the limited time, that's why I decided to cut it short like this. Then the second question, yes, I decided to start with the simple SIR model because of what I'm doing. You know, when I added the arrow, added some other parameters, I discovered that for a layman, the person might not really understand what I'm doing. You know, what I'm doing, I want to go to the financial world. For the financial world to understand this thing, I have to make it very simple. So later on, I'll build on it. I've started doing that already. Yeah.
Because you said Bernard Madoff was arrested due to the Ponzi scheme. So if you are looking at the dynamics, you have to capture all the important parameters. That's all. So don't make it that simple. At the end of the day, someone can be arrested because of that.
Yeah, sorry, I understand what you're saying, because if you look at what I said I was considering, in loss distribution, you either consider the frequency at which the loss is incurred or the severity, that is the value of the loss. So when you are considering the frequency, you're just looking at the frequency of the loss. And if you notice, I was particular about the beta of R, that is those who got their claim. You get it? So that's what I'm actually considering. I was trying to look at the return. Who are those who got their return? Is it possible to get your return? So that's why I didn't add all those things, but I will still add it in the subsequent work.
Okay.
Thank you for your presentation. The first one thing I want to do is a comment, and then followed by a question. For example, like someone asks you a question, and then you say, okay, I didn't add this because for a layman, they will not understand. I think that this is an academic environment, and whoever is here is never a layman. So to have that kind of assumption that layman will not understand, I think that maybe we should desist from that kind of comments. My question is, go back to the model. Where you have the scheme. Go back.
Okay, the model itself?
Yes, here, very good. Now, you are approaching this from an epidemiology, whatever, and my question is very similar to what he says here. If you look at what you presented here, for me, what I see there is just the population, the number of people. Because you say for the first one, susceptible, you look like people who, let's say, want to invest, but they have not yet. You get to the red one, people who have kind of like entered the scheme also, and the last one, the number of people. So when I see that scheme there, it looks like it's just the number of people who are involved inside there. So I don't see how this is relating to how the scheme functions here. So what do you say about that?
Please, can you take your time to ask the question very well?
My question is that if you look at the compartmental model that you have here, okay, what you have there, per my understanding, is just looking at the number of people. If you talk about the susceptible there, you define that is the number of people who want to enter the scheme. They have not yet entered, but they want to enter. Then the next batch is people who are already in the scheme. So now you relate all this to how the scheme functions. And I see that it's just looking at the number of people, like the population dynamics of the people. I don't see how that relates to how the scheme functions. And I'm asking you, what would you say about that?
Well, we are talking about the number of people. That's why I specified that for this distribution that I'm using, we could consider the severity. Please, I want you to understand. Okay, let me just explain. When you are talking about the loss distribution, you either use the frequency, which is associated with discrete probability distribution, or the severity. Because I'm trying to look at human being and money. You know, I'm talking about finance here. I'm just using epidemiological to understand the dynamics of it. So when you're talking about this one, I can use the value, that is the severity, looking at human being, what is the actual money they are getting. For in this case, I'm just looking at the frequency. So it's human being I'm dealing with here, not another.
Yeah, but where is the money part?
Oh, but I told you that I'm not using the severity. I'm using the frequency, not severity. But if I'm to consider the severity, then you will see the actual money these people are putting in and what they are getting. Do you get it now? That's why I said this work is ongoing.
Yeah, but the thing is this. If you look at the model, what I see there is, like I still said, can you tell me what the susceptible mean?
Those who are aware of the scheme but are yet to invest into the scheme.
So at the end of the day, it's talking about people.
Yeah, that's what I'm doing.
So where is the money?
Oh my God. I've explained several times. We know we have frequency and severity. I'm not dealing with the severity, which is the value of the scale of the loss distribution, but rather the frequency. And I think
So you are on TV. You need to control emotions. So the next question.
Thank you. Hello. I believe you cited MMM as an example.
yes, please.
Do you get it? So how did you got to know that MMM is a Ponzi scheme?
Oh, even though you go to the internet and you type Ponzi scheme in Africa, especially in Nigeria, the first thing you see, Marvel Movida, MMM, Bonibus, because of the way it operates. Like I said earlier on, I said we are talking about the Ponzi scheme. The first definition I gave to a Ponzi scheme is any investment scheme that is promiscuously, outrageously high interest rates. And MMM didn't even register under Bank of Nigeria. Do you understand? So from the beginning to the end is a Ponzi scheme because this thing were not accredited, their certificates were not real, many of these things. So they didn't really register under the normal conventional banks. So starting from the beginning to the end is a Ponzi scheme.
Okay,
even the interest rate too.
What's the definition of Ponzi?
Like I explained, there are several definitions of Ponzi. You know, let me start with this. Some normal, let's say a financial institute could be a genuine financial institute at the start. So let's say Bank of Ghana is requesting for a particular percentage, or maybe they're supposed to meet up to a particular standard, and they can't really meet up to this. So what they would do is, for people not to know that they cannot meet up to this kind of standard, they could try to do some forging. So any investment scheme that is being established based on unnecessary forging, maybe their certificate is not real, or maybe what they have put on the wall are not true, or if they affiliate themselves with some big companies that are not real, you know, all those things, anything that is not right is a Ponzi scheme, coupled with the interest rates. Do you get? So it's not only interest rate that characterize an investment scheme to be a Ponzi scheme. Other factors are there.
Okay, so with this explanation, I believe you were here when the men's gold brouhaha came. Men's gold. Okay, and I read it on the internet, and it said something like it was Ponzi scheme. So with this, your thesis, can you say that men's gold brouhaha was Ponzi scheme? Yeah,
funny enough, someone gave me that gist like a month ago. The person came to me that this men's gold, whatever that's, it's a Ponzi scheme in Ghana. I said, really? Okay, let me just go and check it. But I can't really say much about this because when the lady told me, I didn't really go to the internet to investigate more on these people. So for you to know if an investment is a Ponzi scheme, you could use this model to probably use the interest rates. I don't know. What is the interest rate they give?
But like, I have a definition, please, if I would like to read.
Yeah.
I think a Ponzi scheme is a fraudulent investment operation where the operator or an individual or organization pays returns to its investors from the new capital paid to the operator by the new investor rather than from the profit earned through legitimate sources.
Yeah, it's the same definition, sorry. I have this in my work too.
Yeah,
but
I know
it's
that,
from Wikipedia, sorry.
No, it's not. Yeah, I know. But you did mention that if you don't have certificates and a whole lot.
Well, you know what? This explanation I'm giving to you is from several research. You know, I read a book by Lewis, 2015, and that was the explanation he gave. Because he was trying to analyze Ponzi scheme. So he said that when a certificate is not really, then there's this guy to carry 2009, it says something on this too. So the explanation I'm giving to you is something in literature. It's not that I'm giving you, that's the one in Wikipedia. But if you want to look at the Wikipedia, you talk about the fraudulent acts that you said. I know of that too.
Okay, so why the name was named after Ponzi but not
questions. When you have your turn,
please,
just ask a straightforward question, not back and forth, to save the time. So I'll go to the next person.
I wanted to know the assumptions you used.
Okay, thank you very much. The first assumption is that there is no investment into the scheme. That's why I don't have the, the arrow pointing to that from the R to the S. Okay. And the second one is that the population is a fixed population, that is the N is equal to R. That is the second population.
Okay, so thank you very much. There is always a time for interaction. When we have the breaks, you can follow up with questions. So don't be determined to ask all the questions here. We'll listen to the next speaker. That's James Barb Achemfoa on Stefan van Kempten theorem. Shall we welcome him?
Good afternoon. My name is Bachamfo James, and I'm presenting on Cepheid van Kempten theorem. And this is the outline of my presentation. To give a brief background, the concept of fundamental group came up due to Henry Poincaré, who sought to investigate whether indeed the Betti numbers suffice to determine the topological type of a manifold. And so in examining the work done by Enrico Betti, he poses the question that given two surfaces with the same Betti numbers, is it possible to pass from one surface to the other by means of a continuous deformation? And so he tackled the question by choosing coordinates of a point and any p functions of these coordinates, and realized that the point describes a finite closed contour or a loop on the surface. But he also realized that there are instances where these functions do not return to their initial value, but rather undergo substitutions of these functions, yielding different closed contours or loops on the surface, defining the form of the surface. And so this group of the surface is what he called the fundamental group in his analysis etudes paper. Now, comparing and drawing distinction between two or more topological spaces has been and still remains one of the major studies of topology. And if one can identify a topological invariant which holds for one space and not for the other, then these spaces are not homeomorphic, hence distinguished. But if you serve through or consider the known topological properties such as connectedness, compactness, and the rest, none of them seems to distinguish between surfaces such as the Klein bottle, the torus. And so this work seeks to employ an invariant called the fundamental groups. And the objectives are to use fundamental groups to distinguish between some geometric surfaces, and also to use the Cepheid van Kempten theorem to calculate the fundamental group of some surfaces. Now, the method employed is to associate to each topological space an algebraic object, such as a group, so that homeomorphic spaces have isomorphic groups attached to them. And in so doing, the information that one obtains about the algebraic setup gives information about the topological one, hence this concept of group theory. Now, a surface or a topological surface is said to be a Hausdorff space that is locally homeomorphic to the Euclidean plane. And concerning the orientability of a surface, if one traverses around a surface by any path and the direction does not change, it is said to be orientable. And the surfaces are classified based on an orientable surface of genus 0, of genus greater than or equal to 1, and of genus equal to h minus 1, where h is the number of handles or holes on the surface. And, of course, the sphere, the torus, and then the double torus are examples of the surfaces. Now, the fundamental group of a topological space is a set of part homotopy classes of loops relative to a base point. And for one to say that a topological space has a fundamental group, of course, these group-wide properties must be met. Now, there's a theorem which says that the fundamental group of a circle is isomorphic to the set of integers, which is used in calculating the fundamental group of other spaces or surfaces. And these are some helpful definitions used in the work. Now, the Seifert-Van Campis theorem simply talks about decomposing the bigger space into smaller ones or simpler ones whose fundamental groups are known so that they can be used to calculate the fundamental group of the bigger space. And now, considering the torus, it is decomposed into the spaces P, K, and then their intersection. And of course, we realize that P is a deformation retract to its boundary, K has a trivial fundamental group, and then the intersection is of the same homotopy type as a circle. So applying the theorem, we realize that the boundary of P is a bucket of two circles. That is to say that the fundamental group of P is a free group on two generators, which is isomorphic to the two copies of the set of integers. Hence, and the normal subgroup is also given by the loop, which is a commutator of A and B, giving us the expression or the reduced word that we have here, which is abelian. Hence, the abelianization of the abelianization of the two copies of the set of integers, giving us the fundamental group of the torus. Likewise, the Klein-Bottle is also decomposed into the spaces K1, K2, and then their intersection. And again, we realize that the K1 is a deformation retract to its boundary, K2 is simply connected, and then the intersection is of the same homotopy type as the circle. So again, applying the theorem, we realize that the boundary of K1 is also a bucket of two circles, as we saw in the case of the torus, which is to say that it is also a fundamental group on two generators, which is isomorphic to the set of the two copies of the set of integers. But we realize that the normal subgroup here is rather given by a relation which is quite different from that of the torus, giving us, which is x, y, x, and then y inverse, when you traverse around the square that the Klein-Bottle is formed from. And so we have the fundamental group of the Klein-Bottle given by the expression that we see here, the two copies of the set of integers modulo the expression or the reduced word that we had. Now, diagrammatically, the torus is obtained from the square with opposite sides identified and then glued along the directions. And so gluing x to x, we get the cylinder, and then gluing y to y, we also get the torus, with A, B indicating the two generators. Again, realize that if you traverse around the square, you see that y, x in blue color are moving in the opposite direction as opposed to the x, y in the green color, which is to say that, or which is to indicate that it commits, hence its abelianity. And again, the Klein-Bottle is also formed from the square, with opposite sides identified and then glued along the directions. But here you realize that y and y are moving the same direction, but x and x, the opposite sides x and x, are moving in the opposite direction. And to get and to be able to glue them, you have to twist it in such a way that the directions will align so that we can glue them. That's how come we have the Klein-Bottle here. Now, again, considering the double torus too, it is also decomposed into the spaces P, K, and then their intersection. And again, we see that P is contractible or has a trivial fundamental group, and then K is a deformation retract to its boundary, and then the intersection is of the same homotopy type as a circle. And we realize that the boundary of P is a bucket of four circles. When we apply the theorem, it's a bucket of four circles, which is to say that it has a fundamental group on four generators, giving us the four copies of the set of integers. And then the normal subgroup is also given by the loop, which gives us the reduced word that we have here, or the relation that we see here. And so the fundamental group of the double torus is isomorphic to the four copies of the set of integers modulo the relation that we have here, modulo this relation that we see here. And so this is the fundamental group of the double torus. Now, diagrammatically, we see that P is contractible or has the homotopy type of a point. And then again, we see that K is also is a deformation retract to its boundary. And then the P intersection K is also of the same homotopy type as a circle. And we have the A, B, C, D indicating the 4 generators that generates the double torus. Now, considering the 8 figure, we also decompose it into P, Q, and then their intersection, and realize that the intersection has a trivial fundamental group, which is to say that they have a fundamental group which is isomorphic to the amalgamated free product, which is given by the product that we see here. So the fundamental group of the figure 8 is isomorphic to the 2 copies of the set of integers. Now, considering the nth dimensional sphere, it is also decomposed into P, Q, and then their intersection, and realize that P, Q are homomorphic to the n-dimensional Euclidean plane, which is to say that they have a trivial fundamental group. Hence, the fundamental group of the n-dimensional sphere is also trivial with n greater than or equal to 2. Now, considering the spaces that we took into consideration, we realize that they all have different fundamental groups, which is to say that they are not isomorphic. And so giving an information about their respective spaces, that they are not homeomorphic, hence distinguished. And so we came to a conclusion that the fundamental group uses simple connectedness and then the abelianity of a group to distinguish between some geometric surfaces. And these are some of the references that we considered. Thank you.
Thank you. 2 questions.
In fact, well done for your presentation. But please, how will you explain your work to a layman, someone who has no idea about topology and the terms homomorphism, isomorphism, decomposition, and the rest? So how will you just explain to someone who has no idea at all about your work? Thank you.
Thank you very much. The main idea is to consider geometric surfaces or geometric shapes.
It's like geometric face. Someone doesn't know what you mean by that. To a layman.
To a layman, I believe you have seen, you are having a bottle in front of you, which is a shape. You are sitting on a chair, which is also a shape. You have seen a box before, which is also a shape. And so we considered we are looking at how to differentiate one shape or one surface from the other. And we took into consideration topological objects or surfaces of paramount interest. That's how come we have the torus, the climb bottle, and then the rest. And so it is to differentiate between these surfaces. That's how come we
Okay. Is there any field that this particular theorem have been applied?
Of course, there are fields that these can be applied.
Can you give me some of?
In geometry, this can be applied, and then in geography, considering location, because this is mainly about a loop, and a loop is a path which begins at a point and then ends at the same point. And so if, for example, I am here and you are here, how am I connected to you? Or if one is here and then someone is also at the Department of Mathematics, how do you connect with the person? And so it is also applied it is in, like, for example, using the Google map, how they connect or how they are able to know that this person is here, or this is where you are going. So you have your map directing you to the place. So that connection is also, and then it is also applied in packaging. For example, the bottles that you see, the bottles that you see, they all were deformed to give you the shape. And I believe you have seen, for example, you are now seeing different bottles here. They all went through different deformations to give you the different shapes because they are not the same. And so it is also applied in packaging or recycling.
It's maybe more, or not maybe, it's more a remark to the quest for applications here around. It's actually also quite applied in the world of flow in porous materials.
Applied in the world of?
Flow in porous materials. So the topology of the pore space can be very interesting for larger scale fluid dynamics, and also the topology of the fluid phases that reside in the pore space is analyzed with methods from topology, and might help us in developing large-scale equations for fluid flow.
Thank you.
Thank you for your wonderful presentation. I think most of your work hinges on simply connected curves or simply connectedness.
Yeah,
so,
it's a vital component of the fundamental group.
So when do we say a curve is simply connected?
We say that a term or a space is simply connected if it can continuously be shrunken to a point. If, for example, if you have a balloon and you can, or if you have a sphere and you can shrink it to a point, you can reduce it to just a point. We say that it's simply connected if you can continuously shrink it or get it to a point.
On one of your slides, you have what looks like a figure 8 curve turned horizontally. Yeah, something like that. Do we say this is simply connected?
No, we decompose it into 3 spaces. The part labeled by
I'm saying
P, if
you treat a figure 8 curve as a
yeah,
space.
you can deform it to get a point. And so it is simply connected, but looking at the point X naught, that one is a point, but we now we decompose it into 3 spaces. So we have the first by giving us a circle, but that one is not simply connected. And then we have that labeled by K, which is also a circle, which is also not simply connected. It is the point that is which is simply connected.
Thank you.
Optimal insurance, investment problem under stochastic volatility and model uncertainty. And this will be delivered by Bernard Efa Nyako. Shall we welcome Bernard to the podium?
Yeah. Hello, good afternoon. I think we have gone through a whole journey of pure maths. We didn't know where we were. So let's get back to industry and see what we will understand here. Okay, I'm Bernard and I'm presenting on optimal insurance, investment problem under stochastic volatility and uncertainty. Now this is my outline from introduction to the reference. Now, within the insurance company, they really face this challenge of taking decisions. They are overwhelmed with so many factors when they are taking decisions in terms of how to allocate their resources, how to use their resources, where do they invest. They are really faced with this risk of claim because when they take the money, they have to pay back in terms of claims that comes to them. So they use different methods, they use different approach. Some methods they use is reinsurance, which is reinsuring yourself with another insurance company. They also invest in risk-free assets or risk-free investments. Example one we know is the treasury bills to get some money or some interest on the money. Hence, when claim comes, they can pay those claims. However, they are still faced with some dilemmas on how to invest. The question is, how much do you invest? Which claim reinsurance do you take? Which claim, which proportion of your claim should you also invest? Now, these problems are being looked for, literatures exist for these types of problems. Boyan, in 2003, considered an insurer with reinsurance and investment under Houston model, the same as in Agri, but just that he also looked at CEV's models. So my objective for this presentation is I'm considering an ambiguity-averse controller. That is an insurer who is an ambiguity-averse controller. And I'll study it under a stochastic volatility model and allow model uncertainty within a finite time. Now, when I say an ambiguity-averse insurer, is an insurer that prefers certainty over uncertainty. That means he always like to take decision on certainty when he's certain about the environment than taking decision on an uncertain environment. But to begin with, to start with our model, we set up the market, and we describe our economy with this probability space, a complete probability space, generated by 3 Brownian motions. And our financial markets, we have 2 different assets in there. We have the risk-free asset or the riskless asset, which is defined, the price process is defined by equation 1, and that of the risky asset also defined by equation 2. Here, the volatility is seen as stochastic, and we are using the mean reversion approach that volatility will always approach the long-term variance. So we consider 2 problems. Reinsurance has there are 2 types of reinsurance. We have proportional reinsurance and non-proportional reinsurance. So I'm considering 2 problems. One is an investment proportional reinsurance with diffusion. So this is the first problem. Now, our claim process, that is how the claim is distributed or how claim comes into the insurer, is given by the dynamics of equation 3, where A is the rate of claim, B is the volatility of claim. Our reserve process without reinsurance, initially what happens is the insurer will take some premium, which is described as psi naught. And when he has those premium, he has to pay claims that will come. So we subtract the claims from that, and that gives us our reserve process. Now we introduce reinsurance. Now this time, the reinsurance we are talking about is proportional reinsurance, which is any insurance that is agreed by the cedents, that's the insurer and the insurer company, that whenever claim comes in, you pay a certain proportion, and I'll also pay another proportion. So here we describe the proportion here by Q, which is between 0 and 1. Hence, if you introduce such reinsurance, our reserve process will change by psi not being the amount received, the premium that comes in. The insurer also pay some Q proportion of the claims, and psi 1 is the Q proportion of the claim that comes to the insurer. Psi 1 is the amount is going to also pay to the reinsurer. So from there, we generate our worth process, that being our dynamics or our state variable for this problem. That is given by equation 6. And that also is the sum of the whole reserves, and the amount he is going to invest into the risky asset. The amount is also going to invest into the risk-free asset. Now we define pi to be a vector of the 2, to be our control variable here, which we will apply later in the control problem. The next one, let's look at problem 2. That is the non-proportional reinsurance. Now, I took a special case of the excess of loss reinsurance. That is a type of reinsurance where you agree with the reinsurer that when the claim comes in, we are going to fix a certain amount. When it goes beyond that amount, you pay the rest, and I'll take the retention level we have already agreed. So that is excess of loss reinsurance. So that one, we allow the claim process to follow equation 7, where ZI is the claim size that comes in. The reserve process is also defined by equation 9, where C is the premium rate of insurance. Similarly, we are going to subtract the claims from it as well. Then we introduce reinsurance to the problem. Now, to introduce reinsurance to this problem, we define alpha, which is our retention level, and we take the minimum of the claim that is going to come in and the retention. Then we define that one as Z alpha. Now, we introduce this into the reserve process, and that is given by equation 10, followed by the expansion in equation 11. Then this will give us, when we apply the same method we used in the first model, we will get a similar worth process, but differently from that one. Now, the main objective, as we said, was to maximize the expected utility of the insurer. So hence, we set our objective function to be an expectation of the utility of the worth at terminal time. Then we allow the three assumptions we made earlier on is to allow miscalculational errors, that is uncertainty. Now, we are working within a certain space, a probability space, but we are going to allow that the insurer can move freely, he can decide if that reference model is good for him or not. So we build an alternative or equivalent probability measures we are calling kill, that the insurer can move in between. So with that, we generate a new objective function given by equation 14 that takes care of this model uncertainty within it. Now, in equation 14, we realize that we cater for the change in the measure or the change in the probability. What you could see is we have RS, which is the relative entropy, that is measuring the distance or the discrepancies between the probability measures within the space. Then from that, since we are changing the probability space or we are changing the probability measure, our worth or the state process was also going to change when it goes into a new probability space. Hence, we will have a new dynamics for the worth. For the financial process, the risky one, and that's a new worth process for both problems. Now, after solving the problem, we obtained the optimal strategy for problem 1, which is given by equation 17. That is L star being the amount to be invested into the risky asset, K being the proportion that the insurer is supposed to pay or cater for, as in for his reinsurance. Then equation 18 is the value function, the optimal value function that we get for problem 1. Now, C, U, N, T are parameters which we solved and we had those values. Now, theta, T, it's the ambiguity coefficient that measures the confidence of the insurer in the measure he's using. Now, beta is the coefficient of the ambiguity. M and J, M is the risk aversion of the insurer, and J is the value function of the insurer. Now, when we move on to problem 2, we have two solutions, two control problems or two control solutions. One is when the claim size that comes in, when it's less than the retention level, then we have alpha star defined, alpha tilde defined there, and L star being the amount to be invested into the risky asset. However, when the claim size that comes in is greater than the retention level, then it means that the retention level now becomes the optimal, the retention level now becomes the optimal reinsurance policy for the insurer. Now, in general, for problem 2, we will define the optimal control problem or the optimal strategy by equation 23, and the parameters are defined below by equation 24 and 25.
2 minutes.
So we perform some numerical simulations on it to check the sensitivity of some of the parameters. Now, we look at Xi here, which is the premium volatility, the risk premium volatility. Now, we wanted to see the impact on how much the insurer invests into the risky asset. Now, you realize that when we allow the insurer to change or change his measure, or we allow him to be free to change, allow model uncertainty, now the amount he invests into the risky asset reduces, as in from A to B. And the sensitivity of that parameter also reduces in A and B. The next one, we also check the impact of A. The impact of the interest rate, that is the risk-free interest rate, on our retention level. Similarly, when we allow model uncertainty, we realize that there's a reduction in the retention level. And there's a reduction in the retention level, and the sensitivity also reduces over time. So in conclusion, we build analytic expressions for the optimal investment and reinsurance policies, which we obtain. And given parameter values on field, we can always calculate the amount the insurer is to invest into the risky asset, and the amount the insurer is also to invest into the reinsurance policies. Thank you. These are some of my references.
Thank you very much. Yeah. Question time. Question.
Thank you very much. You have educated me. But I want to know, is a reinsurer an insurer?
Yes.
So then I was confused. If there is reinsurance agreement, then let's call the insurer a direct insurer. A direct insurer.
So when there is a reinsurance,
yes,
we call the insurer the cedent, and the reinsurer becomes the reinsurer.
But
there are two names for
in your explanations,
yeah,
I've gotten what you're saying. You are using the insurer, the insurer, the insurer. Is it the direct insurer? Because if there is a reinsurer policy, the reinsurer is also an insurer.
Of course.
So I want to know the distinction between the two.
So the reinsurer insures the cedent.
Sure.
And the insurer insures, let's say, the audience or the agents within an economy.
Policy holders.
Yes.
So which of the insurer are we talking about here?
I am concentrating on the cedents. That's the insurer, not the reinsurer.
But you keep on saying insurer, insurer. So I was getting confused. Okay. So whether you see the cedent or the direct insurer.
All right. Thank you.
The last question. In the probability space that you define,
yeah,
you know that the reinsurer has a truncated distribution.
Yeah.
And the direct insurer has a full distribution.
Yeah.
How do you therefore define the joint distribution between the reinsurer and the direct insurer in the probability space? Thank you, Mr. Chair.
So if we go back to our reserve process, if you go back to the reserve process, when I introduce the reinsurer into the system for problem 1, like this, I define a new cost of reinsurance, that is Psi 1, which takes care of the cost of the cedent insuring himself with the reinsurer. However, there is this now here, which is the safety loading, which is making sure that the amount or the amount of money the cedent insures himself with the reinsurer will not surpass that of the reinsurer. So with that distribution, you cannot, the insurer himself cannot over-insure himself, such that he's not at risk. We put a safety loading in there. In both cases, you see I have nu here, and in this I have mu. So it's a safety loading to prevent them from not going over their distributions. You can't go beyond yours.
The next. No, you first. Okay, go ahead.
All right, that was a wonderful presentation. You kept mentioning probability space, probability space. So it presupposes that you have a sample space, you have a sigma algebra, and you have a probability measure. So on slide 7, no, the slide, before 7, which component gives us our sample space, which component gives us the sigma algebra, and where's the probability measure? Thank you.
Okay, so the usual notation that is used, omega is our sample space, F is our sigma algebra, P is our probability measure.
Okay, so we shall thank you very much. Application of wavelength coherence for the correlations of daily returns of some Ghanaian stocks. This is by Riddle Egan. After that last one.
It's okay. Mr. Chairman, ladies and gentlemen, good afternoon once again. I'm Reda Egan, and I'm presenting on application of wavelet coherence for the correlation of some Ghanaian returns. And there's the outline of my presentation. To begin with the introduction, I would like to say that this research will contribute to literature on the Ghanaian stock market, in which we have more investors coming on board to make investments in our stocks. Hence, it's of interest for us to look at how some of these stocks correlate to each other. I mean, how one depends on the other or not. Now, there has been many approaches used in finding correlation, like the Pearson correlation. But the novelty in this work is the use of wavelet approach in finding the correlation between these stocks. These classical approaches in the economic time series mostly you mostly find the correlation in either time domain or frequency domain separately. But literature reveals that these two components are of equal importance. So we'd like to analyze the correlation using both domains. But the limitation with these classical approaches is that for the time domain, we normally assume that our data is stationary. And for the frequency domain or the spectral analysis, we actually assume that the market activity is stable, which is also not true because buying and selling can sometimes increase or reduce depending on time. So wavelet analysis will help us to combine both the time and then the frequency domain to make this analysis. So there's one objective of the work is to analyze the relationship between some stock returns on the Ghana Stock Exchange using the wavelet technique called wavelet coherence. It's just an analog of the correlation term. So moving on to the methods, wavelet transform is defined as a function with some zero mean, and we say it's localized in both time and then frequency. In this case, we are trying to say that we'll try to decompose the data and actually look at what is happening at each scale of the data, not the entire series. The wavelet transform is just a convolution with the function and then the series defined in equation 1 and then equation 2. We'll also talk about the wavelet power spectrum. This is used to determine the variance happening at each scale of the data set, which is defined in equation 3. We have wavelet coherence, that's to say the correlation, defined by equation 4. In this case, since we are looking at the series according to each scale, we would like to find the correlation happening at each scale of the time series. And we have the phase difference. This will help us to determine whether they are positively correlated or they are negatively correlated at each scale, given by equation 4. So there's a whole lot of mathematical terms in here, so I'll move on to the results since we are interested in that. I chose 3 sectors. I had the financial sector, of which I consider the Ghana Commercial Bank. industrial sector, and the manufacturing sector, of which we have the Unilever Ghana Limited. So actually looking at how these sectors are dependent on each other. It had a time period of 9 years. And we should also take a note that we excluded most public holidays and weekends. So we finally had a sample size of 1,990 trading days for this week. This figure 1 shows a time series plot of the closing prices of the stocks and the returns. Our analysis is based on the returns, so considering the plot of the returns, we could see that GCB has some volatility in its returns, followed by PBC, that's the produce buying company. And then the Unilever having minimal changes in its returns as shown in this figure. We would like to use wavelet analysis to capture this behavior. But I'll first look at the descriptive statistics of their stock returns. The analysis showed that Unilever had both minimum and then maximum returns compared to the other 2 stock returns. This figure shows the wavelet power spectrum for our stock returns. We have a lot of wavelet function, but for this week, we chose the half function because it was suitable for our data set. And then we had a decomposition of 7 levels. We further on divided this decomposition to 3 different scales. We had the very short term, the short term, and then the long term with the various days defined up there. So with the first figure, that's looking at variance or the variability of returns for GCB. And we could see it was captured from 2009 through to 2015 in the very short term. That's where we see most changes happening, or their returns changing at each point. Followed by PBC, we also have a change in the variability from 2009 also through to 2015. The color code indicates blue, which is low variance, and then red, which is high variance. And it also depicts some changes in the very short term. But with Unilever, we saw in the first figure, the changes were minimal. So you could see it be depicted here by the yellow color in the short term. So we see how the variants are changing at every given scale of the series. Moving straight with the wavelet coherence, in that case, we're looking at how they are correlated or dependent at each scale. So we use the same color coding here. Red means high correlation, and then blue implies low correlation happening in there. So where we have the red colors is where we have the correlations happening in there. And we see some arrows in the picture. With these arrows are called a phase difference. They determine how they are dependent positively or negatively. So all arrows pointing to the right shows a positive correlation. That means an increase in one implies an increase in the other. And then arrows pointing to the left shows a negative correlation. Now there's been some up and downwards movements of the arrow, and that one indicates when the other series is leading the other. That's the lead lag term. So for this diagram, I would like to explain this one and use that one to depict the other diagrams. We are so much interested in the short term. That's from 16 days to the 128 days. That's a short-term specification I made. And we could see that over the years, correlations was not actually positive throughout, as maybe a person correlation would have depicted there's a positive correlation at the long run. But we see over here that there's actually some changes. At a point in time, there's a positive, and at another point, there's a negative correlation happening in there. And we see when one series is leading the other in that specific scale. But at the long run, we don't see much happening in there, but there's still some positive correlation in there. The second diagram is for GCB and then the Unilever. The same analysis is being depicted here. With a very short term, we see some correlation happening, and then they are positively correlated. But over here, Unilever was leading GCB at that specific time and scale. That's from 2011 to 2014. So the same analysis could be used in PBC and then Unilever Ghana Limited, still in the short term. This is a wavelet correlation coefficient we had at each scale of our time series. Since much wasn't done in the small, short term, and then the long term, we'll consider the short term over here. That's where I had the color code red. We saw that there's some kind of positive and negative correlation coefficient happening there. This is just to confirm what was happening in the graph I showed earlier on. So in the long run, we would like to say that it's quite more risky to make an investment or holding period for a short term compared to a long term or a very short term. So in conclusion, I'll say this research has been able to combine both the time. The time scales is referring to the 2 days, 4 days, 30 days and stuff. And the frequency domain has to do with the scaling down into a short term. That's the different time horizons, whether a short term, a long term, or a very short term. So we've been able to combine both the time and then the frequency domain to analyze what is happening to our investment. The wavelet approach was able to decompose this data. It wasn't entirely the whole set. It actually had to do with the important part of the data, which means it was actually doing away with noise. And at each scale, we're able to find the variance and the correlation at each scale. So my advice to an investor is that since they want to know the relationship between other stock or other companies to invest in, it will be quite appropriate to increase your returns and reduce risks by investing in stocks which have low correlation. This is a reference to the work. Thank you very much.
Thank you, Ms. Issy. Question time.
Question.
Okay, after that, Richard.
May I? Hello. Okay. Please, can you go to your graph? Any of them? Maybe the biggest one. Like, yes. Okay. Can you explain to us what is really happening here? The variables and the directions, what are they?
Okay, as I said, the directions are called phase difference. They are actually telling us, we see the red is correlation, there's a correlation in there. But we want to determine whether they are positive or the correlation in there is negative.
What is positive?
Positive correlation implies an increase in one.
No. What's the correlation? What's between what and what?
It's between Ghana Commercial Bank and then the produce buying company. That's for this graph.
What in Ghana Commercial Bank are you comparing? Is it a building or?
They are returns.
They are okay.
Yes, please.
So please explain to us, because this graph, I don't know about all of you, but it looks very complicated and complex. So maybe if you can take some time and explain to us what is really happening inside.
Okay. You know, normally with the Pearson correlation we use, over a time period, let's say the same 2008 to 2015, we could have just one value determining the correlation. We end up saying it's positive correlated over the long run. But in actual sense, it's not so. It's actually changing given a particular time over the entire period. So that's what the wavelet is trying to do. It's trying to tell us, it's trying to show us that it's not actually positive throughout the entire period, but there's a change in there that's capturing some discontinuities of which the other classical models were not able to capture. And this one also has to do with using the useful information, because it's a convolution. So where this function convolve with, where there's a similar properties, that's where it picks it up. When it goes to the next scale and there's no similarity in there, it assigns a 0 number to it, which means the information there is not useful. So in this case, this wavelet is actually doing away with noise. As other classical approaches do not, we have to transform it to be stationary before we work with it.
Now the graph.
Okay. So I said the color scheme is blue, which is low correlation, and then red, which is high correlation. But since most people do not invest in very short term, that's the 2 to 16 days, we are much interested in the short term, that's the 16 to 128 days. So where we have, in 2009, we see there's a correlation in there. Then the arrow is pointing right, and then okay. In 2009, we see there's a correlation happening in there. and the arrows are pointing right and then downwards. It implies that at that point, there's a positive correlation happening in there with GCB, with our PBC leading GCB at that particular stage. But when we move across the same time scale to 2013, there's still a correlation happening there, but there's a change in the correlation. They are now negatively correlated. That's the negative direction of the arrows. The same thing applies to when we move to 2015 or 2014. We see there's a change in the correlation. It's still moving, okay, it's still to the left, which is still negatively correlated with our GCB now leading PBC at that particular point in time. So that's what the color and arrows are shown in there.
Thank you very much.
Thank you. Yeah, Richard.
Okay, my first concern had to do with the kind of data you compare in your series, but then I think it has been answered. It has been answered partially. But then the other thing has to do with, you made mention of the fact that you do away with some of the data. So if you are comparing at every point in time, how do you determine which one to take away and which ones to compare?
The function I'm using, that's the wavelets I'm using. That is what it's doing. I'm not the one like taking away the information. We know most financial data mostly come with noise. So it's like a filtering. That's what the wavelet function also does here. It's like a filtering method. So it actually do away with the noise and then come up with the actual data which gives the information. So which means we are representing the whole data with a small set. It's like a population as sample. We make reference to the population using the sample. That's what the wavelet is trying to do in here. We don't need the entire data set to describe the behavior. But you can look at the specific component or the interesting part to describe whatever is happening in there. So that's the doing away with some of the data. Thank you.
Easy, wonderful presentation. I have two questions. The first one is on your mentioning classical models not catering for some correlations. Is it based on literature or based on the fact that you wanted wavelet to favor the other classical methods? And what are those other classical methods? That's question one.
Okay. With what I said with the introduction, most of the time when we are trying to analyze financial time series, we try to make it stationary, right? That we assume the variance is constant, the mean is constant. But in actual sense, that's not what is happening. There's actually some changes going on.
Yeah, before you proceed, that is not always true, because we have heteroscedastic models. So you may want to dissociate yourself from that.
Some of the classical, I didn't say all.
Okay.
Yeah.
So why wavelet and not those ones that cater for the non-constant variance?
Okay. Like the spectral analysis, when you use a Fourier analysis to make any time series, it's actually we are not able to combine both the time and then the frequency domain to make that analysis. Meanwhile, they are all important. We would like to know what is happening when we group them. That's the frequency aspect of it. So it's only wavelet that's able to combine these two domains. For Fourier series, for Fourier transform, I'll just have to look at the frequency dynamics, and which will not capture time, but they move hand in hand. Yeah. So that's why I use the wavelet approach.
My second question is on the returns data. I presume it's from the GSC website.
Yes, please.
Did you consider them on daily basis? Maybe on the 1st of January, you pick returns for GCB, returns for Unilever, returns for PBC, or you just run for a specific length?
No, they're actually daily returns.
No, my point is, even in the daily returns, GCB may record a return on the 1st, PBC will not record a return on the 1st.
Yeah.
Then Unilever may also not record a return on the 1st. So if you consider the time span, are there not some inconsistencies in the putting them on the same level, actually? That is my question.
That's why I said the data excluded the major public holidays and weekends. So
you see, you're not minding me. My point is, you have a generated data set
Yeah.
with equal length. But my
Yes.
point is, they were not all on the same days. Most of the time, we could just try that after your presentation. And you realize that you could have GCB giving you a return on the first. PBC may not give you a return on the first. But because you gave maybe 1990 to 2000 and this, yes, you're going to have a data length where you'll be forced to put some going to 0, because actually most of the returns are 0.00. That is my question, actually.
Please, could you go back to your correlation graph again, the wavelets graph?
The wavelets graph.
Yeah. All right.
Okay.
So
This
yes.
one.
Yeah. Thank you. So you, for example, you said in 2009 you have there's a correlation there. So you using GCB and then PBC, and then you say there's a correlation. Like what does that mean? What's the physical interpretation?
Okay.
Yeah, so you are using correlating their returns, and then you say, okay, 2009 we can see a correlation. What does that mean?
Okay, thank you very much. Correlation here implies we want to see if they are related in some way or they are linked, they are dependent on each other. So if I know they are dependent on each other, how are they dependent? What is their relation? Is it positive or is negative? That's like the term here, correlation. So I don't know if I've answered your question. So if I want to invest in GCB, I would like to know whether GCB and then PBC work hand in hand. I would like to know whether their work affects each other. If not, then I could go ahead and then make any investments in any of them. That's the choice of, that's the main reason behind finding the correlation for an investor.
Yes. Thank you very much. I think for normal correlation, we normally look at the strength of the correlation. I don't know why I'm seeing weaker correlation values. Probably because you said you were taking it at each particular point that generated to that. But with those weaker values, can I still conclude that there is a positive correlation?
Yeah, no, in normal sense, we actually say correlations between -1 and +1. And when it's skewed to +1, we say it's highly correlated. And when it's skewed to -1, we say it's highly negative correlated. So if it's not really near -1, then it's, let me just say, it's still correlated. Like there's still some correlation.
But can I use that for analysis? A strong analysis.
Please come again. Can
I use that for a strong analysis? As in,
no, to get a very strong analysis, it depends on the kind of data you are choosing. I could have just used one sector and look at the companies in that sector, and that one I could have gotten a very strong diagram than this one. Do you get it?
Optimal allocation of university shuttle terminals using genetic algorithm. Michael Asabre Domfre. If you know Kamsef, you don't need you here. Good.
Good afternoon, ladies and gentlemen. My name is Michael Asabre, and I'm doing a presentation on I'm doing a presentation on optimal allocation of University Shuttle Terminal using genetic algorithm on behalf of myself and my colleague, Yahusu Ajiman. This will be the outline of our presentation. So please, I would encourage you to sit tight and enjoy the presentation. Now, I would like you to imagine a scenario where you live in a community that there's just one terminal. And every morning you get up and you have to just join this crowd to be able to get to board the bus to wherever you are going to. Now, whilst this is going on somewhere, there is also in another place where there are a couple of buses like this as a bus terminal, and there's just one or two people in the bus terminal waiting for the, one or two people in the bus waiting for the bus to get full for the bus to take off. Now, I don't know, but then I believe that there are people in this room who can bear witness to this kind of frustration that goes on. I want to give you another scenario where you come out from your home and you have to walk long distances before you get to the bus terminal to board the bus. Or better still, you alight at a bus terminal and you have to walk like a quarter of the traveling distance back to your intended destination. And then finally, I want you to look at a scenario where you are at a bus terminal and everywhere around is like bush and trees, and you feel so scared, wondering if someone will just come out of the bush and attack you, like the lady over here in miniskirt. The emphasis is not on the miniskirt anyway, but the fact that she's frightening about where she's sitting at. Now, as interesting as it may seem, this is going on our various campuses. Not only on campus, also in our communities. As a matter of fact, it's going on everywhere. So perhaps you are wondering why this is so or what is happening. Let me try and help you out. It's simply because there are no optimally allocated shuttle terminals. Now, in the course of the presentation, I may be using shuttle and bus interchangeably, so please take note of that. We will try to understand what it means to have an optimally allocated shuttle terminal in the course of the presentation. Now, the task of actually finding an optimally allocated shuttle terminal is a peculiar problem in mathematics, and it's referred to as the bus terminal location problem. So in the bus terminal location problem, there are some factors that we have to consider. First of all, we'll have to consider what are the locations that can serve as bus terminals. What are the relative distances between these locations, and then how many people are around these locations, among many other factors that we may have to consider. So perhaps you are wondering if what I'm doing is mathematics at all. This is a bit of mathematics to whet your appetite. This is a simplified form of the bus terminal location problem. The objective function is the one that has been shown in the expression labeled 1. Now, on the objective function, the relative distances that I spoke of in the previous slide is captured in the CIJ. And then also the number of people around a particular location is also captured in the DJ. And this objective function is subjected to some constraints that are labeled in 2, 3, 4, 5, 6, respectively. So to solve the bus terminal location problem, we are going to use a popularly known algorithm, which is the genetic algorithm. Now, in 2008, Kafaki and co. defined the genetic algorithm as shown in the slide. This genetic algorithm uses theories of evolution by natural selection. And that is a principle by Charles Darwin's survival of the fittest. So you can see a tiger trying to devour a zebra. So in our case, we are just looking for terminals that are strong enough to survive at the end of the run of the genetic algorithm. Now, to go through the stages of the genetic algorithm, first of all, we have to do an encoding. And in doing the encoding, we are going to represent the locations as genes. So, as you can see from the illustration on the slide, the first location is the first gene. The fourth possible location is the second gene. And then the seventh possible location is the third gene. So a combination of these terminals will be referred to as the chromosome. So after the encoding has been done, we get to the main stages of the genetic algorithm. The first stage is the initialization. We are not going to use the entire set of chromosomes. We will just sample a few of them, and then we will use it. So that is what is done at the initialization stage. And then we move on to the evaluation stage. The evaluation is done with the objective function to actually determine the fitnesses of the chromosomes. And then we move on to the selection stage. There are various types of selection stage, but then we used a type of the selection, which is the roulette wheel selection, and that considers fitnesses in doing the selection. Now, after the selection stage, we go through the crossover and then the mutation stage. I told you that in the initialization stage, we only sample a few from the entire set. So for us to be able to explore the space, we have to do some crossover and mutation to have the other chromosomes which are not selected to be able to be catered for in the algorithm that we are using. Now, after the crossover and the mutation stage, we'll go back and do the iterations. Now, when we get an offspring from the crossover and mutation, we compare it with the parent chromosomes. If it appears that the offspring are better than the parent one, we replace them. But if they are not better, then we just maintain the parent one in the sampled population and then continue with it until we have a stopping criteria met, and then we terminate the algorithm. So in our study, what we did was that we selected 20 possible locations on KNUST campus. So the locations are the ones indicated in the yellow stars. And after the selection of the 20 locations, you realize that it's not everywhere that can serve as a bus terminal. Just because you want to do a bus terminal, you don't just break down an entire building and put a bus terminal there. So you have to do that selection. And then when you are done with that, we run the genetic algorithm with this. So running the genetic algorithm with this, you realize that in the early stages, we had, from here, in the early stages, we had a particular chromosome which is corresponding to this fitness dominating. And then after a while, it changed to this one, and it maintained throughout the generations that we did. Now, because the genetic algorithm is probabilistic, we don't just do it once. We can't be sure about it. So we did it 100 times. And then you realize that on the 100 times that we did it, most of the time we had the solution converging to the one we had in the previous slide. And then for some few occasions, we had different solutions. Those are the ones indicated in the blue lines. So those ones, we said they were non-optimal. And then we concluded that the one that dominated most of the time was the optimal solution. And this optimal solution corresponds to the locations which are indicated in the red stars. Now, interesting enough, after we finished with this research, we realized that on KNUST campus, they were constructing some bus terminals. And it appears that the bus terminals that they used was quite similar to the ones that we had. So perhaps they used our approach, or the person who supervised the project had a mathematical eye in doing it. So we would conclude that we have been able to represent a physical problem with mathematics, and we have also been able to solve it to obtain an optimal terminal locations. And these are the references that we listed out. Thank you very much.
Questions, please. This afternoon, you are on fire.
That was a wonderful presentation by all standards. Thank you. Can you go to your problem with the constraints? You may take the question as a trivial one if you like. Equation number 6. Your problem, the problem itself. Okay. Maximize this subject to that. Okay, 5. Why do you need Xij to be greater than or equal to 0?
Okay, actually our Xij was our decision variables. And what it was doing is that it's actually trying to tell us if choosing a particular bus terminal can serve better than others. So let's say I have 3 locations, and I'm choosing one. That one that I'm choosing, is it capable of serving the other 2? Because I'm choosing at the expense of the other 2, right? So what we did is that we, first of all, they are like probability values. So they are not negative in the first place. They are not negative. So like what we are doing is, we are just trying to limit we are just trying to limit that decision, that it shouldn't be negative. Yeah, they shouldn't be negative. Let me just say that.
Please, may I come in? Yeah. I took part in the project, so I would like to contribute a little bit. The Xij, as he said, is the probability of a person choosing one node over the other node. Let's say you have 2 locations close to you. What is the probability that you go to node A over node B? So there are probability values, and they can't be less than. That's the space we use. You can't not, yeah. So it's either 0 from between 0 and 1. That's
once you say it's probability value, that answers it. Yes.
Okay. Thank you very much. When you were explaining genetic algorithm, the process slide where you're talking about initialization, evaluation, selection, you said that if the offspring is better than the parents, then we move to the next one or we stop. But how do we know which is better? Because you also stated in the slide, when you're showing the graph, that you said that we saw that they were non-optimal. How do we know the ones that are better and not better?
Because of the objective function, which is used for the evaluation. So we've done the evaluation of the chromosomes. Because I hope you understand the term chromosome that I'm using. So once we've done that one, we know their fitnesses. So if we do crossover and mutation, and then we realize that the one that we formed is better than the parent, then we replace it with the parent one. And then for the case of the graph, you were asking, please, can you come again with the graph?
You stated that you found optimal and non-optimal solutions. So it's basically the same question, like how did you find the...
Yeah, with the graph, like I said earlier, the genetic algorithm is probabilistic, or we can say it's heuristic. So we have no guarantee of getting an optimal solution, but then we are looking for a near optimal solution. So what we do is that we do the thing for a couple of times. So you just choose the number of times you want to do. But then when you do it for many times, it's like, let's say, yeah, when you do it for many times, then if it converges to a particular solution in many occasions, then you conclude that, yeah.
Yeah, please, can you go to your map, your GIS map? Yeah, so the yellow stars represent what?
The selected possible locations that can serve as terminals.
So how did you select it?
That was what I was saying, that the selection, you can't just choose anywhere to be a bus, to be a possible location. Perhaps there's a building there. So this one, the selection, we did it based on our own judgment.
Okay, so you didn't go there physically to select?
No, they are GPS coordinates that we took from Google Map.
Google Map, okay, so let's go to the final map. I just want to get a very good reason for what you did. And the red one represents what?
The ones that have been selected after running the genetic algorithm.
So what about the physical one, the one the guys did? Did you also overlaid on this?
The one I said they've already done.
Exactly.
That one, I can't tell whether they used this or not. But then,
okay, because you could have gone there to pick a GPS location of that and then superimpose on your work. And you will be able to estimate the error, right? You should even have to tell us whether they use even a differential GPS or not. And maybe your work is not exhaustible. You could still do that, right? Or you could have even done physically, gone there to do it and run a model and then make that correlation, right? But fortunately, you've done it. So you could go back and pick them, preferably with a differential GPS, and then you superimpose on your model and then look at the error margins. That's my suggestion.
All right, thank you very much.
For the model, I mean your objective function and your constraint, the xij greater than or equal to 0 is an assumption, whether it's probabilistic or whatsoever it is. It's an assumption. And then okay, let's go back to your models again. The y, is it also part of the constraint?
Yes.
Then
the y is just a binary variable. If it's chosen, it's 0. If it's not chosen, it's 1. Right? That's what it's doing.
Oh, okay. So f does not really depend on that. The f in the objective function.
The f is a decreasing exponential function. What it's doing is
no. I mean, does it depend on the y? Is it a function of the y?
No.
Oh, okay. Okay. Thank you.
Okay. Yeah, good.
Okay. The last question.
Who said that?
I thought I was the last person. Okay. Before, at the beginning of your presentation, you've shown us some pictures that depict some kind of problem at the terminals where people will be there waiting for a bus, and then some terminals will have no people there, but the bus will be around. And I was expecting that in your algorithm that you run, you tell us that, okay, due to this and that, then we can solve that problem with this and that. But I've realized that your algorithm mainly concentrates on how to assign terminals to bus stops, or how to assign bus stops to, how to make bus stops, in fact, actually a terminal. So I want to know how your model can actually solve that problem of those pictures you've shown us, because in KNC campus here, I think we face that problems. You go to some terminals, there are no buses, you see a lot of people. Other terminals, so you see buses just standing there, but the people are not there. So how are you going to solve that problem?
Thank you very much for your question. With the issue of the number of people at the bus terminal, I said that will be captured in the DJ, which is in the model. The DJ is the number of people that are entering or leaving. So let's say the number of people around that location. So it's assumed that they would just come to that place. So if we consider that, then we will be able to at least cater for the fact that at some locations, there are just quite a few people there. So it wouldn't cost much to have a terminal a bit further away from them. As in, it would be better to have it closer to where there are more, or where the place is more dense.
Chairman, if I may understand. And just to clarify your question, the real problem is multi-objective. You need several different optimization methods to solve them. They've just solved one of them, which is the terminal. There's a routing algorithm. There are so many of them. So to solve that set of pictures that he puts there, it means you need different optimization methods put together to solve it. Okay, yeah. So that's just one location of terminals. Thank you.
I was just a bit curious. The pictures you used, one of them, the bus 242, reminds me of my days in London. That's fine. But I don't know why you didn't get any local pictures at all. We ran a shuttle service here on campus, and those conditions you are talking about, we have them here as well. So at least you should have gone around, take a few pictures, and let us relate to the work. On that note, thank you all for coming today. And thank you. Announcement.
Yeah, Mr. Chairman, thank you. Please, I would like to remind ourselves that those who have not presented their slides to Patricia, please do so if you are presenting tomorrow. And because of the numbers, we would like to start tomorrow exactly at 9. And please, those who have presented, don't leave, because we have further discussions after tomorrow and then thereafter. And concerning our industrial partners who are with us, please, if you have your problem set, please put them together, and if you can, by tomorrow, alert us so we can begin the discussion. We'll be very grateful. Thank you.
Thank you, too. So tomorrow, 9 o'clock, we want to thank all of you for coming. Have a wonderful evening. God bless.